So I'm starting with the first question for this bookstore. So this first part we are, as I already mentioned in the details of the workshop, in this session I'll be giving an introduction to computer vision. What is computer vision, which are the fundamentals, and how we can use machine learning, in particular deep learning. We use deep learning for vision application. How many of you have attended deep learning classes? I know some of my class students are here, and others. Yeah, first year or second year? Third year. Okay. And computer vision, any computer vision related courses, image processing, digital image processing, computer vision. So this will be very from very scratch, very fundamental, giving you an overview, a kind of a crash course. Within 1 hour of time, you will get some idea about this. But don't restrict only this learning. You please extend and work from. Please mute your mobile phones. Okay, keep it in silent mode. And so you can work further on top of that. And then in the second half, sir will be giving robotics so that you can give the application also based on whatever we are learning, the vision aspects and the deep learning based computer vision tasks. You can apply to robotic applications. Okay, so that's the core idea. And now I'm starting with the fundamentals. Okay, so this is an overview of my presentation. I give an introduction, a bit of history. So what is vision and how it evolved over time? And I will give a use into neural networks. What is deep learning and how we can use deep learning for vision applications? And various applications. Computer vision, which are the different computer vision tasks that you can go for by using this kind of deep learning algorithms. Will give us glimpse of our here in SRM, we are hosting a Center for AI in Computer Vision in UBH12. And you can visit also and collaborate with us. So we will be giving a glimpse of one of the different kinds of works, different kinds of projects that we are hosting over here. History. Yeah, history. The bit of history. So, what is history? What is history? Biological vision. So, when it started. So, all of us know vision is one of the more important human sciences. So, we are using for our everyday life, for navigation, for grasping things, for manipulating, for understanding each other, right? Of each other, right? And for everything, most of us, all of us, we are using biological vision, right? So, comes to the power of evolution, which happened around 540 million years ago during Cambrian explosion. That is the origin of the vision system which came into the biological world for the first time. So that is why we have such a high level of vision system in the biological world compared to the bipedal motion, language systems, or any other kind of the characteristics of the biological world. We can see that vision is very, very high at a high level other kind of features. So during all this, you might have heard of training, right? Training the data. All these years of 140 years of training has happened over these years. That is why we have such a high advanced vision system in the biology. So, neuroscientists in the late 50s, 1950s, 1960s, they started to question why we have, what are the technique behind this vision, whether we can understand what is the science behind it, what is actually happening in the vision, how humans are experiencing this, and what is the neural basis of vision. So this vision can be connected with the brain activities, okay, and how the visual information is controlled. So this was the fundamental concept. The neuroscience. Okay, so neuroscience people started asking. And this was one of the seminal works. But they trying to understand how the visual cortex is working, how the visual is being captured in the brain. It was something around cats. So they put some electrodes in the anesthesia is the chemical, and then try to understand how the stimuli is acting upon the perception of the cat. Okay, so what was the observation is that when certain particular patterns, like edges or curves or the bodies, so certain patterns where activating certain neurons in the brain. That was the main observation. Okay? So certain patterns, they could activate very specific, that was not random, very specific in the brain, in the virtual the complex, the visual complex of the camera. And then important observation as well the spatial invariance. So this kind of a pattern was strong. Certain the receptive field in this area would activate certain parts in the brain of the cats. And also this hierarchy was also being observed. Hierarchy. The pattern was in a hierarchical phase. The pattern in the brain, in the neuron pattern, how will it get activated? It had a hierarchy of learning. So certain layers were getting activated, then another layer, so on and so forth. So there was a hierarchy thing in this. These are experiments. This was one of the very first, and they got Nobel Prize also for this in 1980. Now, this was actually putting a platform for various studies in both the neural world and in the AI world and computer vision aspect in particular. To learn and understand more on how we can reproduce this kind of features, this kind of activations in the machine artificially. Which has led to the computer vision and artificial intelligence based computer vision. Now, what computers do? All of you know we are doing computer vision and image processing. What computers do actually? Systems. Yes. So images are just numbers. What we are taking a photograph in the camera. Once you are processing in your machine. The system is seeing it not as a cat or a dog or a human, it's just numbers. If you have a picture, which is a register, it will be ranging between 0 to 255, 256 of the range. It will be seeing each picture as a number ranging between 0 to 255. Okay, so these are the numbers to be 187, 116. Then, given this particular image, now we need to apply certain algorithms on top of that and process it. So it's very simple. Be human and other animals. We are doing it so unknowingly, right? Very natural process. We are not understanding how we are doing this vision, but in order to mimic this in the machine, it's really hard. There's a lot of processes happening. Vision is not just understanding the object. It's also understanding and comprehending the field. I told in my class in the previous unit. So it's like when you are having a picture taken in a traffic signal. Okay, when you have a driving scenario, you may you may see car and a traffic signal, traffic light, people ready to cross. So you are thinking the picture, it's not only about the car and the person, we are understanding the speed at which the car is moving, the traffic signal, we can anticipate, okay, the car will be stopping, the person will be crossing. So, so it is giving a real-time understanding of the speed. Right? So it's more on a confidence. So that is why the computer vision is a bit more to the comprehension level. It's not just image processing. It's more on understanding, not only processing, but also understanding. And there are different computer vision tasks. So classification, what is image classification? You are classifying, right? What do you have in the image? So when say, okay, out of person cars, car, tree, what is that particular image is ours? Okay. And regression, what is regression for us? Huh? Predicting, right? You are predicting some numerical values. The regression is you have a previous value, you are predicting a numerical value, right? And tracking, localization, so many tasks are there. For that, again, let's go back to understand how you are doing all these tasks. What are the basic necessity and how you are reaching that point to do some tasks. What is the foundation for that? So the very important thing, the prior step is feature understanding, feature detection, feature extraction. What is a feature?
What distinguishes an image from another?
Yes, the characteristic. Yeah, the characteristic of the descriptor. What is distinguishing one thing from another? Yes, the character. So in the car, when you are looking at a car image, you know, okay, because it has this particular shape, it has tires, it has so how you are distinguishing face, you have eyes, you have nose. We understand. How to make the machine understand this? To have some patterns, we have to recognize the pattern, we have to understand that pattern. Okay, then once the pattern is going to be looking for this picture, you have to identify the pattern is identified, maybe a face. So this kind of patterns, understanding these features is the fundamental thing in this computer vision process. And the presence of a feature or not, that is what distinguishing from a particular image or not. Okay, and okay, we know this feature is what we need. How to know which is the feature?
We can define a set of classes.
Define a set of classes. Classes
are supposed in this case in the labels.
Yeah.
When we look at an image, what do we want?
What do we want? So you are saying, okay, in the case we may be looking for knowledge, some transfer knowledge. So that is what the main knowledge is. We already know it. This. The surface of moon is looking like, or in Mars, how it is looking like. We may need some domain expertise in that aspect. We may need some space scientists. They may be knowing, right? Some scientists. We may need some expert knowledge. In the medical field, like the kidney. So we may need this kind of some domain information also from the domain experts. So whichever way how we are collecting the data, as we know, okay, these are the patterns we need to find out in an image. Then you are understanding the features, then using that to classify. But is it as simple as I say? Why? Why not?
Because of machine, right?
All of you should respond, not only one, okay? Yeah, please.
Okay. On its own is a dummy entity by nature. We have to input the
We have to input. Suppose I'm telling my machine, okay, it should have a face, it should have an eye and a nose and it should be looking like this circle. But whether that will be okay? So I'm keeping the camera here,
Yes.
but you can see only the hair of the person sitting behind you. In that case, I don't see the eye, I don't see the nose, I don't see the lip. In reality, that is the problem. And the illumination. Some people who are sitting in a dark part, I may not be seeing, the camera may not be seeing. Okay, so there are a lot of practical challenges as this. Viewpoint variation. We will be taking the photo. You are training a lot of photos taken in the front mode. What is the text? Taking the photo on the side view. And we get it completely different from your training data. So viewpoint very completely changed. Then as I told occlusion, see that occluded so that you will not get the whole features. Lighting conditions may change. Very small, sometimes very big. The same can also bring some challenges to the same. Class variation. Within the class itself. Intra-class and inter-class. Intra-class variation is itself. It can be in those ways. Different kind of scale. So all these are the problems when you start the features. So for this purpose, how to make robust feature extraction. For that only, so many feature extraction techniques has come in the past, in particular to image processing, computer vision. So many algorithms. My students, this is the handcrafted features. Okay, we will be handcrafting the features. So we manually tell. Okay, we will be manually telling. Okay, these are some of the features we are interested to look upon. So we are trying to look for 6 features. Once we get these kind of features, then we will be applying some machine learning techniques, say like SRMIST or K-nearest neighbor algorithm. Or they may be in the image, and we connect it in the page. Now that the features, now you start using same context, it's another kind of feature extraction. So this was happening the last decade. So 90s till 2010 years, people are doing this kind of tasks, developing some this kind of features and understanding them, and then applying on startup techniques, which are understanding. But we may be missing out some important things. We don't know whether these features, what we are deliberately posing, whether they are the right one to go for, or are we missing something? Or can we make the machine learn these features all by itself? That was the next question people were trying to. So now you may be knowing, is there a way? Yes, what is that way? Yeah, there are some convolutional neural networks. So basically RNN, LSTM. So these are nothing but the neural network based approaches, deep learning based approaches. So we are trying to move this. Is it possible to learn the features directly from the data instead of hand engineering? Yes. So we are trying, this is the solution. We are trying to use deep learning approaches where we have neural networks. Every layer of these neural networks really learning some sort of features, right? Using different layers of filters, it will be trying to learn different kind of features. So in this layer, it may be learning very low kind of information, very some structures, some the next layer, we will be analyzing some block level information more. Getting a more higher level abstraction, abstract level information, so that has should have the face, eyes and nose, all these things. Is it clear? All of you, what is a feature and what is deep learning? How deep learning is applied? Yes.
Can we have unlimited number of layers whenever we want to pass?
It's not unlimited. There are some, yes, we can have n number of, but it has certain problems if we use n number of unlimited. So there are certain problems. In order to avoid that, there are new architecture designs which can have better performance even with a limited number of layers. I will come to that. Okay. And why now? See, okay, after 1950s, this vision technique started, people were interested in this. The first works on deep neural network is happening in 1960s. And this propagation was developed in the 1980s. 85, 86. But why this kind of now? Deep learning AI hi-fi. It's just the right? So we have such a different discoveries of data, the internet and the data set. We have new resources, high-end computing power, thanks to the gaming gamers, game developers, yes. So for that, the circuits move randomly. So they develop GPU. So we have ultimate high-end power and NVIDIA series. Right? Then what is anything else? The data and the GPU. The need for the application, the need is there, we also. Yes, exactly. So the application also lead to the necessity is a right? So the necessity became everyone has more access to the gadgets. We are having camera system, computers. We have the power to use this also. Became ubiquitous, right? So that also made this accelerate. Anything else?
As we made the shift from heuristic-based artificial intelligence in the 1950s to complex level architectures and various relevant frameworks.
Yes, exactly. Frameworks. So machine learning was happening, as I showed you earlier, different kind of development features that happened. And frameworks, people started developing so many new things, new frameworks, and now we have access to PyTorch, TensorFlow, open access to Python, right? Python, PyTorch, all these open resources became available. Different softwares became available. Right? We have more access. We are using that. There's also one unseen hero is that we have some other open platforms which we researchers, but it won't come in the name, but unseen heroes, GitHub, repositories, archives. So in weekly basis, new reports are coming, new archive papers are coming, which are actually accelerating in such an unprecedented pace. Okay, so this was not the scene in some 10 years ago. When we want to write some paper, we have to wait until the paper is published in the conference and then to come in supposedly. But now, something within 1 week it is in archive. People have GitHub, they will release the code, right? So this is all these have accelerated the momentum. So now data, hardware, GPU and software, quite a lot of frameworks, all these things are accelerated. Now, having said that, now we will have a glimpse into the neural networks, how this deep neural network is working and how we can use it for vision in particular. I'm going very deep, but at a higher level, I will give you a picture. Neural networks allows us to directly learn. As I told, we need not handcraft the features, the layer, and automatically by itself. Then, which is the fundamental unit This is a single layer network. So these X1, X2, up to Xn is the input what you have as you have into the system, and it will be multiplied with certain ways. It is the parameter, W, and this index. This will be multiplied WX and plus P, which will be a minus WX plus P, will be between one answer, which is the output Y of X. So in terms of this, is equal to W. Transpose it with W, you are writing the subject. And similarly, you have multiple neurons in this layer. This layer is known as the input layer and output layer. You can have hidden layers. So you can have in between layers, that's also hidden layer. So from one layer to the subsequent layer, you are connecting all these inputs. That is why the name fully connected neural network. You are fully connecting each and every input to another neuron. So here is connected, so you got one of X. And all others you are connecting with a different way, you are getting Y2 of X. Then you are connecting this blue lights and the set of waves, you are getting Y and X. So this way you are fully connecting all these inputs to a neuron in the next layer. Using the same equations, and Y of X is equal to W plus P. Okay? But is there enough chemistry service of X for what is this X? Function of something. So it has a particular name in the paradigm of neural network, which is activation function. What is activation function and why do we need activation function?
It is non-linearity into the data.
Yes, you studied everything.
Yes.
Okay, and don't come into the class. Okay, so introducing non-linearity. What do you mean by introducing non-linearity? What do you mean by non-linearity? So, if you have only linear combinations, WX plus B, so this, it's not learning anything new. You are linearly combining, again, you are linearly combining. Okay, you can linearly distinguish, you can cut a linear boundary to separate it out. But what if you have some non-linear data, which is the de facto in our universe? Most of the data is not linear, it has lots of complexity in the data. Yeah, so suppose you have the data like this. You have some data like this. Can you apply any linear boundary to this? No, you will need this kind of boundary. So if you apply only linear combination in every line, every layer, yeah, you cannot bring this non-linearity. So in order to deal with this problem, there is this activation functions are introduced into the network. So we can be applying non-linearity. So you can separate this out. So there are different kind of activation functions that we commonly use. Sigmoid is one function, and everything is another function, multiplication is another function, and furthermore, gain is there, P value is there, plus, that's how. So many are there. Okay, but it has some pros and cons. This is one of the different standard that we will be using in these learning programs. So the linearity is incorporated with the help of activation functions. So this is the input layer, we have hidden layers. So once you connect all these here, from this layer onwards, again you will be connecting from this one, this one, this one. You will be connecting again to the next layer. So likewise, you can create multiple layers. In each layer, you have multiple neurons. And likewise, you can have any number of hidden layers. And this is how you will be developing a neural network. What is the name D? So in reality, you will be having a lot of hidden layers. Let's say 50, you have 50 hidden layers. You have 150 hidden layers. Right? So you have that many numbers of hidden layers in between. It's very easy. That is why the name is neural network. So this is the basic form where you have the single hidden layer, but you can understand you can have lot of hidden layers in the discussion. So once you compute this output layer, so you will be getting some sort of here. You will be getting some sort of features. Okay, so features will be getting some sort of features will be coming here. So you can actually some find the activation from some sort of function will be getting and will be getting some result. Now you will get the output here. And in the training data, you will be knowing some true values. What do you mean the true value or the actual value? Ground truth. You call that ground truth. So given the ground truth values, okay, given this, it should be telling, okay, this is a cat picture. Okay, so when it should come to the cat, it should be 1. It should be in other classes, it should be 0. But it's not coming that way. So whatever you are getting more predicted values, predicted data. So so what will you do? You will check the predicted value and the actual value. Predicted value compared with the values. Predicted what is the loss function you are getting, which is nothing but error. Whether you are getting, whether you are getting the answers correct or correct. After having this loss function, what is the next step? Okay, so till this point, I will give you another term for this until this point. It's called forward pass. Forward pass. So the term is forward pass. From here, from the input until this point, you are passing it forward. And after getting this, so what will be happening in the reverse? Backward pass. So this backward pass is known as propagation. The thing is back propagation. You are propagating the values, gradient values you will be propagating backwards, and this is where the most interesting step is happening in deep neural network, where you are updating the weights. So you know we have learned these weights, W1 and W2, but this is not giving you the perfect result because there are some loss. Now you need to tweak it in such a way that it is matching with the ground truth. It should be approaching close to the ground truth value. If it is close to the ground truth value, what will be happening to the loss? Loss will be minimum. It should be reducing. So our ultimate goal is to make this distance to be very similar to the ground truth and to reduce the loss. So how to reduce the loss? You will play with the parameters. You will play around this weights. Yeah. So you will be trying to change this value. Okay, maybe this is not the exact correct weight we need. We need to tweak this. We need to tweak this value to some support. So we will be tweaking these values, adjusting these weight values. So how to do that? Can we do it for all? Each and every take each and every W and then try root force? No. So for that, we are doing this back propagation technique. So that is a back propagation technique to optimize the weights. You are optimizing the weights of the parameters without this back propagation. In this back propagation, you will be learning the gradients and optimizing using some optimization technique. One very famous technique is gradient descent algorithm. You might have heard of gradient descent technique. Yes. So what is that? Is there are many more. Adagrad, Adam, Nestrov. There are many more, but this will be the standard popular approach that we use. And in this back propagation, you will be computing the gradients at each step. The gradient of the loss with respect to that particular weight will be computed. So this is Yeah, let's call this loss function as J. Let's call this J. What will you do? We will compute the gradient, dou of J by dou of W. That is the gradient of the loss with respect to the rate. Okay? Then once you compute the gradient of the loss with respect to the rate, you will obtain the rate. Okay? Instead of W, now you are changing it in such a way that it will be obtaining the rates. But how do you know whether this is the right one or not? So technically the figure here is a representation of the layer of the activity. Okay, here that we have some point in this. My example in the class. You are in a mountain, okay? You are carrying some points. You are somewhere in the middle. The target is to dash their loss. Minimize the loss, right? So you have to go to the bank, you want to go to the base station. That is where imagine that this is the base station, which is the base of the group. So how will you achieve that minimum point of loss? You want to be here. So this is the top. First you will check for the gradient. You check the gradient. You are at some point you check the gradient. What gradient will be telling you is the direction of upward. It will be telling where the upward direction is. So currently over here, it will be telling okay, this is the direction of the gradient. So what you have to do to go in the direction of gradient? In the opposite direction of the gradient, because your target is to go to the minimum. So you take a step in the negative direction. That is why this negative sign here. So you are taking a step in the opposite direction of the gradient. Okay. So you are thinking you are at this particular range W. You are taking a negative step in the direction of the gradient, and you are taking the weight. Okay. So far you reach here at this second point. Now what is it? So then we will be checking the gradient. It will be telling you the direction of force. Then you will take a step in the opposite direction. So this process will continue until you reach the value. This is clear?
Yes.
This is the back propagation step happening. How you are doing the weight update. So you will be finding out this you will be finding out the W value. And we will be checking at what point we are achieving the minimum loss. That particular value. So, what is the meaning of R? The meaning of JW. That value of W, which is giving you the minimum of loss. That is the optimum W star. Okay, so you will be finding out that particular value of W, which will be minimizing the loss. Okay. So I think I am taking a lot of time, but I will be skipping it. Sometimes I will skip. So this is the source of neural network. Topic was computer vision. How to apply the neural network for vision. So can we directly apply it here? So you can see here we have each one as in a vectorized form, x1, x2, x3, up to. So it's a single vector. It's a single vector. So think of an image, you have a 10 by 10 picture, 10 by 10 image. Once you vectorize it, what will be the size of that? The feature, 100 dimension maybe, 1 by 100. So if you are processing definition, SD layers, it will be some so the number of parameters using the vectorizing those kind of large things is very accurate. Because the parameters will be millions of parameters system. Okay. And also another thing, what is parameters is something, and another thing are the some of the very important characteristics of images. That is also very large. If you do not conduct the advanced cryptography. So what do you mean? So what do you mean by the spatial information? The base temperature, how the structure of the information is. So we know, okay, I should come here, that knows, then no, what will happen if you're vectorizing the information corresponding to the mouth is coming somewhere at the end, the information corresponding to the eye is coming somewhere in the first section. The last information is completely lost. It's not we are interested. We are interested in vision. The system should learn the information, the spatial information also, right? Once you are applying this fully connected, you are using this spatial information and the number of parameters also is very high. To overcome this, one specialized form of neural network has been developed that is known as convolutional neural network. So, very similar to the fully connected neural network, but what distinguishes is that you are applying a particular convolution at this stage. What is the name? Convolutional neural network. You are applying convolution with the help of filter. You are not processing the whole image at once. Instead, you will be using a part of image. The part of the image will be considered, and that will be multiplied with certain weights, which will be, you can imagine a matrix of 3 by 3. Okay, that 3 by 3 will be taken, which will be a filter. So how many weights will it be? You will be having? Yes, because everyone is just one scalar. Now I am telling you, you are using a filter. So 3 by 3. How many weights you have? 9. 9. It is a filter image. Okay. So you are applying this filter onto this patch and you convert. And it will be ending up in a neuron at this level. So the similar kind of convolution you will be doing it in the sliding window, meaning you will be starting from this leftmost corner on the top, then you shift one step and again you do this convolution. Again, we will be doing it the next step, so on and so forth. I have a video here. You can see this. It will be doing the convolution. Instead, second from here, then one step, and I'm going to the next row, and the third step. So accordingly, you can see the values, how the values are changing. So this is the input. This is the filter. So this will be convolution. So this is how you will do the convolution. Then after convolution, another interesting component that we'll be using is the pooling technique. Pooling. That's pooling. So why this is used? It doesn't have any learnable parameter. It's not using any weights.
It uses a match for weights.
Yeah, no weights. It's not using any weights. It's not a learnable thing. But it will be simply doing a compression. It's a dimensionality reduction technique. So suppose you have a feature map like this. What will you be doing? You will be pooling. You will be taking this. First to go to what is the maximum value? 6. The second top, what is the maximum value? 8. Here. So without losing much of the knowledge, you can imagine this will be in a higher dimensionality. This is just a sample of a smaller dimension, but it will be in a very high dimensional space. So if you are doing this kind of a compression, you are reducing the dimensionality, then you are keeping the spatial variance also. You are keeping in compressing in the corresponding regions. Right? So this is the pooling technique. Then in between, you will be using some sort of this activation functions. So you can see a diffusion, review is nothing but an activation. Then max pooling. Then convolution, review, pooling. Convolution, review, pooling. This kind of repetition will be happening. Until you reach the final stage where you will be the output, then it's the same thing. You compare the layers, and then nothing over it. So in between layers, It's the only thing that you have the distinction from the fully connected, but here it's very interesting. You're doing conversation very fully. Is it clear to all of you?
Yes.
Yeah. So once you are doing, once you're done with this conversation, this is where the feature learning is happening. At the beginning, we are learning. The machine is automatically learning which are the important features. And once you do that, you can apply it for any kind of vision task, like classification or segmentation or detection, whichever you are interested in. Okay? And classification is classifying which is the particular class of that image. So every one of these images, they have an image like challenge.
Yes, sir.
How many of you know that? Yeah, others, please go and check what was that, because this was the one which revolutionized all this deep learning methodologies. It was the Alex was the first one which actually realized it was the French methodology. So this is the based on this image challenge, many different kind of these neural network architectures has come. In 2003, it was software machine learning, okay? Like SRMIST of the everything. Here, exactly, you can see the error is to 18. Now, this thing is 7 what happened to me? 17, doing it. Exception. And 15. 15 nothing. It's let's okay. Restless game. See, if outcomes of human error is 5.1%. Using restless in 2015, surpassed this performance, human performance. It's very something 3 months. But at the same time, as you were happy in the beginning, you can see the because that's how it is going. You can see that. Exponentially, it has increased. But there are some pros and cons for that. It can be increased. So, it has to do with the ranking gradient problems. Okay, so we can't use that. And express some architecture and novelties have come later on. Like as I told you, instructional models, learning within the layer, and ResNet, some skip connections. Then came transformer. Have you heard of transformer?
Yeah, correct.
Yeah, but you read this paper, attention is all you need, right? So this is the 2018 paper, and so many advancements happening in the last few years, 5 to 7 years. So you should get acquainted with the happenings in this field if you're interested. So as I was saying, you can do classification and other tasks. Other task is segmentation. Is segmenting out that particular object part alone. That is the segmentation. How it is different from detection?
In detection, we only want to study the main subject of the image. In segmentation, we study the environments who contours.
Yeah, taking the edges of this particular object, but in this case, it will be the output in terms of the bounding box. In object detection, will be a bounding box will be the answer. You can show the bounding box. Happening, summarizing, so many things are happening. With the large language model, so many things are happening. But these are also fundamental things. I'm not going in detail, but you can check. Because based on each of these tasks, there are very number of segmentation. FCN is a network. UNet is there. SegNet is there. Then deep lab models are there. Okay. Similarly, object detection. You might have heard of YOLO.
Yeah, YOLO.
YOLO. You only
You only
Live once. No, look once. You only look once. And then RCNN, different family of RCNN. RCNN, fast RCNN, fast RCNN, mask RCNN, and SSD model. So many detectable models are there. Have a look onto that if you are interested in any of these computer vision tasks in particular. Then if you want to learn sequential data, now until this we were talking about image. Once you have one image. So you suppose you have a sequence of data, as in an example in the computer vision, where you have a sequence of images. Video. It is nothing but a collection of frames of images, right? So in such kind of a situation where you have a sequence of data, you will be using some sequentially adaptable model, which is RNN, LSTM, GRU kind of model, which not only uses the current input, but also the history from the past. The internal memory also will be used. So one application you can see image captioning. Image captioning, you will be capturing the image and then you will be using some models on top of that to have a final output. So image captioning is an example, the action, robotics is an action application, right? One is doing on that. So these kind of things will be using a sequential so many variety of applications. So today we are going to see one of the applications how we can use this knowledge on computer vision and this advanced deep learning techniques for the application in robotics. Okay, so we can apply in various apps. You can use in the robotics and in the self-driving car. The potential is very, very immense. You can use in various fields. Now, 5 minutes. I'm left with 5 minutes. In 5 minutes, I give a glimpse of what we are doing in the SRM ISC in our lab. In computer vision. Here we approach and very specifically computer computer vision. Various fundamental algorithms and applications of machine learning with a focus on computer vision. Responsible layer. What is the responsible layer?
and with the ethical layer.
With certain ethical aspects of that. In almost everything. But how to make it human compliant, how to make it understandable to human, and whether are they the correct one to rely on. And because we are also working in collaboration with various organizations. One of the problem when we initially started talking with them, DRDO and all, we were asking what are the kinds of problems where you are using AI. They were telling we are not using AI at all. Because we can't rely on a system. That is from the defense people, that's what they told. Because how do we know whether these 99% accuracy is actually 99? What about that last 1%? Even the ones that we are getting the right answers, are they really right, reliable and robust? So this reliable thing has a very important role to play in the current era where it is very and all are using it without any kind of control. Right? So this reliability and trustworthiness is what is coming under this responsibility. And in this particular under this particular umbrella, we are working on some explainer systems. We are really explaining, okay, this is what our model is learning. This is how the model is giving you the results. Active learning. Active learning, as we were initially telling the experts in the field, how the scientists, space scientists know about the space information and more about the planets and all. Similarly, DRDO scientists, they will be knowing about the mine. Map was telling plants are coming, right? So it is some of them are not distinguishable. In the case of mines, we cannot understand whether it is real mine because it is sonar, it won't capture. It won't get it. So my solar is working in solar system. We have been working in so the scientists were telling sitting and we are watching DRDO lab. I think this kind of even in a simulated platform, it's very hard because you can't understand with the highlight part. You can understand with the shadow part. Okay, so sometimes it is not, you haven't seen this mission in post. I forgot the
artificial intelligence.
Yeah, using the mind, yes. So it's almost impossible to understand some of the features. So sometimes this feature may be important, sometimes the shadow may be important. Okay, so all these aspects are quite interesting. And meta learning is another thing. Meta learning is what we call huge learning. We don't have the huge collection, access of a huge collection of data. One thing is you can very few data to your hand. Technique. That's a problem because when you do something data in that huge amount of data, very minimal confidentiality research, you will not get. So even if you are having small amount of data, you will still achieve good performance. That's learning with some organizations, we completed it already. I'm not going into the detail, but if you're interested, you can go to the website, and then you can find more website also. All these papers what we have developed based on this. Yeah. That we developed as a part of this project. Tomorrow we will have a hands-on session on this. Simulator using the Lisboa platform. Okay, so basically, there is when we started working on this, we realized that there is no data set to study on what to do. There is no sonar. Whatever we have, some Chinese data set, but it's very, very minimal. That also, there is lack of data set. And even from Indian, we can go there and work, but they won't give analysis to our data. So we were in a position to develop something on our own. So we developed this, yes, in a simulator platform, understanding how they look like. We simulated in a using that, we try to mimic how it will be looking like in a sonar environment. And we came to notice that this is one of the very first, right? The first sonar simulator data set globally. So we are still, we are curious about that. We are waiting to make it available publicly. So this is one of the this project. And these are some of the that we have been publishing. And let's have a look at using a human in the loop, which is active listening strategy. Human in the loop, getting the domain expertise from them, putting them also in the loop. We don't want AI to go in one way, human intelligence to go in another way. Artificial intelligence should be augmenting the human intelligence, right? So we are trying to put this particular active learning algorithm where we can complement both of them, both of the intelligent systems can complement and we have the best of the world. So this is the idea and that particular item for the research and we developing some of the different ones on data set which is calculating data set. So we are doing segmentation tests. Now we are doing segmentation. Yes. You are getting the boundary, which is the water body, which is the medium, which is the vegetation part, so on and so forth. So this is ongoing. And another work is on medical clinic. I think we will have minimal amount of data. Still, actually, the best person. Meta learning strategy is being used. Meta learning is used to understand ML, prototypical data. So using that, even the data is very minimal, can make the system learn to learn. That is the learn to learn, and the system can still produce the some of the data that we collected from Athira hospital. Yeah, there some additional miscellaneous work. I'm going to go into the details, but if you're interested, please visit us. Please visit our website. You will have more information here. And you can scan and go on the website and see that we are using available. And if there's other commercial interest, so you can be published. So learning journalism, so this is about the summary. This is a summary of the benefits and how we can use the deep learning models. And other vision class. How the vision aspect combined with the deep learning, how we will be using our lab related and project related work. Okay, so this is our team. I'm getting my previous team in the afternoon. This is a picture for my PhD days. And this is based to have independent robotics. And yeah, something very interesting. If you're interested to collaborate more on projects, you can contact me. Thank you very much. Any question?
Yes, that human in the loop technology is supposed to work as a particle for every response that the artificial intelligence model generates, right?
Yeah, it's a checker and also some to so this can also act as a not only checking, not only validation, we can use input also. Yes. So for example, the scenario is like you are having the kind of work that you are doing is you have a way of data that you are getting from satellites. But we don't know which one to process first.
Yes.
Maybe some of them are very informative.
Yeah.
Some of them are completely images. So how do you know which one to go first?
We need someone who is
Yeah, so that is the place we are getting the expertise of the domain expert third candidate. So what will we doing? We use some sort of an AI.
Yeah.
AI algorithm.
Yes.
We will initially try to sort it out. Okay, maybe this are okay. There may be some this uncertainty in this part. Can you please help me out? So define from the million of data, you will initially use some uncertainty techniques like entropy and say some 100 or 1,000 of images. We give it to the expert, ask them, okay, which one to go for first. So for them, it is okay. They will be telling some 5 to 10 images. Okay, you study with this first.
Yes.
So it's like hand in hand of the machine and the human.
Yes.
So that we can bring out the best rather than checking everything and finally bringing out after a long time. We can really shorten this process and with high performance.
This is anyways the best methodology to do training on the model, keeping all the ethics and morals in mind. Some companies push for a super intelligent artificial intelligence.
Super intelligent, I didn't get you. General intelligence. AI. Okay, about super intelligence.
It's like the God tier level of artificial intelligence. Bring artificial intelligence.
Yeah, do we really? Yes, see, all the people have a body in we need AI. It's the highest value people. But we are not yet there. We are not getting the general intelligence stage. It's but it has everything going on through some course. So that is why this responsible AI and all these are getting a lot of importance nowadays. Maybe in our lifetime itself we'll be reaching somewhere. I don't know yet, but yeah, definitely it will be augmenting. AI should be augmenting the human intelligence.
Yes.
That's my knowledge and my
yeah. Starting something else. Analyze that quantum something even beyond that. Like that cloud set, for example, they have lava lamps. and the camera. With every moment itself.
Okay, so we'll discuss that in the break time. Okay, now it's a break time. You can have it and come back in another 10 minutes of time. We will have another interesting session by Okay, thank you.
Okay.